I want to go back to a topic that we discussed earlier in the course, and I highly recommend that you go back and review your notes for this. Transformations of functions. We talked about three different kinds of transformations of functions: shifts and stretches and compressions and reflections over one of the axes. And we talked about how when you do something directly to a variable, then you are making a horizontal change. Horizontal changes are counter to the intuitive direction. And when you do something to the entire function, we are making a vertical change, and vertical changes go in the intuitive direction. So let's start off with a function like sine x, which we took a look at in the last video. And let's graph y equals 2 sine x. So I'm going to draw another set of axes here. So here's y equals sine x. Here we're multiplying something by 2. We know when we multiply something by a positive number, it is a stretch or a compression. Then we want to ask ourselves, is it a vertical thing? Is it a horizontal thing? Well, we look and see, are we multiplying just the x by 2, or are we multiplying the whole function by 2? We're multiplying the whole function by 2. And so that tells us it's a vertical change. Vertical changes are in the expected direction. So if we know multiplication by 2 is a stretch or compression, you would think that 2 would be a stretch. And in fact, it is. What we're going to do is take this function and stretch it vertically by a factor of 2. Everything is going to get twice as far away from the x-axis as it was before. So let's see, if that's height 1 and there's height 2. This point right here at x equals 0, it's at y equals 0. It's right on the x-axis. If we move it twice as far away from the x-axis, if we move it twice as far away from the x-axis, it's still on the x-axis. It doesn't go anywhere. This point that was at height 1 now moves up to height 2. So at pi over 2, I'm going to keep these x values lined up. Pi, 3 pi over 2. You could have done this all in the same set of axes if you liked. So this point that was 1 unit above the x-axis now moves 2 units above the x-axis. This point's right on the x-axis, it stays right on the x-axis. This point that was 1 unit below the x-axis, it goes now 1 unit more below the x-axis, down to 2 units below the x-axis. And this point's right on the x-axis, it stays there. So what we've done is we've taken this picture and we've stretched it. Points above the x-axis go up, points below the x-axis go down, and we end up with a vertically stretched sine function. It has the same period as it had before. So the period is still equal to 2 pi. The amplitude, the distance from the middle to the top, or the distance from the middle to the top, that's been stretched. The amplitude is now equal to 2. It was 1 before, now it's 2. If this was a sound function, and you went from this sound function to this sound function, so you've probably seen a sound wave before, the period is exactly the same. The frequency is exactly the same. This would be the same tone. It would just be louder. Let's take a look at another transformation of y equals sine x. Y equals sine 2x. So starting with sine x over here, I multiplied the whole function by 2. Here I've multiplied just the x by 2. See if you can decide what that does to the original picture. I'm going to write some axes again. Feel free to pause the video anytime you want and think it over. So we know that multiplication by 2 constitutes a stretch or compression. The 2's right in front of the x this time, so we know it's a horizontal change. Horizontal changes go counter to the intuitive direction, backwards from the intuitive direction. So you would think that 2 would be a stretch, like it was here, but in the horizontal sense, it's always backwards. It's always backwards. So instead of a stretch, it's a compression. So let's see, that's height 1. We're not playing around with this thing vertically at all. It's a horizontal change. -1. Pi over 2. Pi. 3 pi over 2. 2 pi. And if we're going to compress it, every point is going to get twice as close to the y-axis as it was before. This point's right on the y-axis, it stays there. This point at height 1, it's going to stay at height 1, but it's going to get twice as close to the y-axis. Instead of being at x equals pi over 2, it's going to go twice as close as it was at pi over 4. And this point that used to, it's right on the x-axis, it's going to stay there, but it's going to get twice as close as it was before. Instead of being at pi, it's going to go to pi over 2. This point at height -1 is going to stay at height -1, but it used to be at 3 pi over 2. It's going to get twice as close to the x-axis as it was. We're compressing, so it's going to go to 3 pi over 4. And this point that used to be at 2 pi on the x-axis, it will stay on the x-axis, will get twice as close. It'll go to pi. And we end up with a function that looks like this. This function keeps oscillating forever, and so does this function, and so does this function. If we wanted to draw another oscillation, we could just as easily do that. It would complete 2 oscillations in the time that these 2 complete 1 oscillation. So this time we haven't done anything to the amplitude. The amplitude is 1. The distance from the middle of the curve to the top and the middle of the curve to the bottom is 1. We haven't changed it. What we've changed is the period. We've compressed it by a factor of 2. So instead of being a period of 2 pi, it completes a complete oscillation in pi units now. So going from the original curve to this curve, it has the same amplitude. We haven't made it any louder. If this were a sound wave, this isn't any louder. It still maxes out at 1 and its bottom's still at -1. What we've changed is the period. We've made it oscillate faster. When you make the period half as big, or in other words, when you make the function oscillate twice as fast, for those of you with a musical background, you'll know, or you may know, that all you've done is, if this is a note, you've gone up 1 octave. So if this was middle C, this is the C right above middle C. Whenever you double the frequency or make the wavelength half as big, make the period half as big, you've gone up 1 octave.